Test. Yeah. Hello, everyone. Thank you for joining us today. So I would like to introduce you all to Juan Orduz, who is a data scientist at Woltz from Germany, joining us today. And he will have a talk about time series forecasting with NumPyro. And we will have some time for questions later if you have any. So with no hesitation, please join me for welcoming him here. And yeah, the floor is yours.
Thanks. All right, can you hear me well? Okay, so yeah, I'm very happy to be here. I want to share with you my experience working with time series forecasting models in the probabilistic setting. So take this as my journey, and this is by no means, let's say, how we should do forecasting, but I just want to present some challenges and opportunities which might be helpful for you. So this is the outline of the talk. So I want to give a brief introduction to what motivated me going into this subject. And I'm going to talk a little bit about the kind of the code behind it. In the description of the talk, you will get a lot of references, and all of the code is published online already. So I would rather not focus on the code that much. I think let's focus on the concepts. And on the first part, I want to just talk about classical forecasting methods and how to map this into, let's say, the probabilistic setting with NumPyro. So we'll talk about exponential smoothing and ARIMA, and also intermittent demand or like time series, which are just time series which have a lot of zeros. And in the second part, I will talk about the opportunities on which I've seen and believe that like this type of approach to time series forecasting can actually be very useful. And at the very end, I will briefly talk about some work that has been done on the PyMC lab side in the context of time series analysis. So yeah, the slides are already there. I'll share the link later, so everything and the reference should be there. So to start with, I've been working time series data for a while. And my first exposure into the Python ecosystem is stats models. I don't know if you've noticed, but this library, it's really, really nice. It has a lot of statistical tests. The documentation is quite nice. And it offers the classical time series model like exponential smoothing, ARIMA, and it's quite nice. This is just a screenshot of the documentation. The API, in my opinion, is a little bit hard to get because it's not really unified. But there's a hidden gem, which is what is called the unobserved components model, which is a state space model. And if I would need to go for like a univariate time series forecasting model, actually this would be the first thing I'll try, just because it's very easy to fit. It gives a lot of options like adding seasonality, adding regressors, and a dynamic trend. And there are many kind of options on. You can see that in the documentation. For example, I can have like no trend, I can have a local trend, or I can have like a random walk. So it's very, very nice, and actually I don't see a lot of people talking about it. I think it's a really good baseline, especially for univariate time series. But recently I've been faced with the problem of having not one, not 100, but thousands of time series. And of course, you could do like a brute force for loop on the stats models time series, but it's definitely not scalable. And recently, well, not recently, I would say a couple of years ago, this Nixla kind of forecasting universe has become quite popular, and I really, really like their work. So this is a snapshot from the GitHub page, and they have time series, classical time series models in the stats forecast library. They also have ML forecast, which is leveraging on top of machine learning models. They also have some deep learning models in your forecast, and also they have this hierarchical forecast on which they'll try to reconciliate if you have many time series that they should add up consistently. So actually, it's super nice. It integrates with polars quite well, which is something that I enjoy quite a lot because I love polars. And we have been able to scale this in a production-like setting because you can actually parallelize the training with orchestration frameworks like Ray. And let's say we have been able to train, I don't know, 50 or like 100,000 time series within an hour. And the stats forecast library offers, I would say, most of the package and the models that it's available on the stats model. So if I need to start doing a forecasting project, I will look into Nixla. Again, this talk is very opinionated, so this is my strong opinion. And especially when you're running baselines, let's say if you have nothing, which is the case that I had, then these packages offer seasonal naive or like the last point prediction, which are really, really the first thing you should look into. But for some problems that I'm going to talk later, I wanted to have a little bit more control on my model. So I had a baseline running in production, it's fine, but can we do better? And better in the sense that forecast at the very end is not just doing forecast for the sake of forecasting, but usually you're going to take this forecast to do certain type of optimizations or something downstream. So I come, again, this is another bias from the probabilistic programming world, and I discovered this forecasting module in Pyro, which is a probabilistic framework written in PyTorch, which was developed at Uber, but I think now it belongs to, I think, could be that it belongs to the Linux Foundation. I'll need to double check. But anyway, it's very popular, and within the contribution model, they have a forecasting module, which gives you the availability to really run your custom model, and a lot of the cross-validation and prediction boilerplate is handled for you. So I decided to give it a go. I had to relearn another probabilistic programming language, but I was up for the challenge. But since I was coming more from the PyMC world, I actually had experience with NumPyro. And NumPyro is, again, a probabilistic language model inspired in Pyro's API, but it's written in JAX. And it's actually very good for kind of Bayesian inference, which I mean MCMC and Hamiltonian Monte Carlo. So I was thinking about, should I just try Pyro or should I just keep with NumPyro? That was my dilemma. But then I saw this post by Kyle Karen, and I had been in contact with him just sporadically on like private messages, and he published this really, really nice article about how he was using NumPyro to simulate and optimize out-of-stock levels in supply chain. And I saw this like, okay, this is fantastic. So, and he did everything in NumPyro, and this is one of the problems that I was facing, that I had out-of-stock problems and also censoring, in the sense that a lot of these items that were forecasting simply were out of stock, which means that we could have ordered more, but they were just simply the ceiling of the shelf. So at that time, I decided, okay, let's go with NumPyro. How hard can it be? And this is the first model in the NumPyro documentation. And this is why I was always thinking about going to Pyro, because to be honest, in spite of the fact that I know that because I'm a maintainer myself, that maintaining documentation example is hard, this was a very hard entry point for me. So I had a choice to make, and I decided to give it a go. And today's talk is about my journey on how to disentangle and make sense out of it. So we are not going to talk about that model. We're going to talk about something on its core. And when you see the NumPyro code in the documentation, you see a lot of stuff. But one thing that is always present in the forecasting models in NumPyro is that they have this scan function. And the kind of the signature and the way it works is rather cumbersome. But the main idea and its power is just that it's a very efficient way of running for loops. And if you think about forecasting, what you usually do is to take your previous data point, do a transformation, and move to the next one. So you need to iterate over, let's say, your time series. And you could use a for loop. No one is forbidding you to do that, but that's going to be very inefficient. So that's why both, let's say, in PyMC and also in NumPyro, they have this scan function. And I don't know much about the internals about scan, but what I can tell you is that it's significantly fast. So my tip is if you want to look into this type of models and you feel overwhelmed about the documentation and the examples online, just crack scan, and I'm going to show you how, and then the other things will make sense. So yeah, let's do it. So what scan does, it's a, let's say this is what would be a Python implementation of scan. So it takes a function, which is going to do something on the iteration. It's going to take an initial set, and then XX is the array that you will iterate. So think about maybe as the time component. So you start with a notion of a carry. So you are going to carry, and you start, you're going to carry the results kind of recursively. So you start with your initial point, and then your x, y, s is going to be the results. So you start looping over xx, and then you apply f, which is a function which depends on, let's say, your current state, and the state before. Let's think about that carry. It's the previous data point your time series, and do something, and does something. That thing should return kind of a new copy of the carry, which could be just simply go ahead in time, and y is your one-step prediction. And then you will append this to the results, and then you will return carry and the result as well. So as you move along xx, these carries will change, and the recursion will follow. That's it. But the notation, it's not that easy to understand, so let's go through a specific example. So let us assume that I'm going to compute the following thing, which is the sum of powers. So I have a variable phi, and then what I want to do is compute 1 plus 5 squared plus 5 cubed plus whatever, h plus 1 times. So if I want to do in Python, I can do it just like this. Range, take the powers, just give me like a generator, if you will, and then you just sum it up, right? So how would this look in scan? So again, the sum of powers, the assert statement just showed that what we did makes sense. So the sum of powers in scan, you need to define these transition functions, which depend on your carry, which is where you're going to, kind of what is going to be iterated, and also on your phi. And you can add any other parameters that you want. And this is something that we actually find quite a lot in the NumPyro documentation, is that this carry can be many things. So in this case, what I'm going to carry with me during the iteration is the sum, let's say the previous sum, and then the power at the point where I need to do the operation. So this is just taking the previous state. So then what you do is to take your power and multiply by phi, and then you sum that by the previous result. And that will just do the update on the next iteration. It's a very cumbersome and pedantic way of writing a for loop, but doing it like this is the way you can actually speed things up in NumPyro. Once you have written your transition function, then you can run it, so to say. So you can pass scan, then you have your transition function. Your initial state is 0 for the sum, because the sum at the very end has nothing. And the 1 is the power, because something to the power of 0 is 1. And then you just iterate over your arrays, which is just this vector of phi values. And trust me, you can do it compute it by yourself. This is the same thing as above. So the important thing here is to really crack the transition function, because if you do that, then kind of the rest will follow. If this doesn't make any sense, it's fine. It took days, I would say weeks for me to make this work, but I want just to show you the gist that within these big models, where you should focus is in these transition functions. So let's take a little example. So this is a beautiful data set which I generated myself. Also, a lot of these kind of experiments were done in synthetic data set, where I control the true values to have an assessment on how good or bad the parameter recovery and the forecasting was. And we have a very simple train test split. And what we would like to do is to forecast on the test set. So one of the classical time series models, which is very good and a very good baseline, is what is called an exponential smoothing. Is it? Okay. So what I want to do in exponential smoothing, at least in the simplest version, is the following. So I have my y, is my time series variable that I observe at time t. Then I want to do the forecast in the future, h steps in the future. And I just want to generate that forecast, assuming I just have information on the time series until time t. So how do I do that? There's some kind of latent variable that is called the level. And the prediction is going to be a weighted average between let's say, the current state of my time series and the previous level. So it's pretty much like a clever weighted like moving average. And this is surprisingly very good baseline. And the alpha parameter can vary between 0 and 1. And this is what we call exponential smoothing, or like a level model, because we have one variable L that does the job. So if I would like to implement this in NumPyro, the only thing that I need to really think of, well, not the only thing, but the main thing is the transition function. So let's see how we do that. So again, we need to define what the transition would be. So we have the carry state, and we're going to have also this tag by the time t. And the carry, let's say what I need to remember from the previous point is just the previous level. So I call that previous level because carry is a horrible name. So then I need to update my level, which is the second step. So Tmax is here kind of the size of the time series. So if my t is, let's say, already beyond my horizon, I just forecast the previous level. And if I'm not, then I just write this formula, which is just translating the math here, like the alpha, the previous level, and the y. And the alpha I call here level smoothing because I want it to be verbose in a bigger model. So that's just literally translating this step. But this is where kind of we have a nice twist within the probabilistic programming schema, and it's the fact that now I can assume that this prediction is the mean prediction, but I can assume that this comes from a distribution. So we're going to assume that our, let's say, errors are normally distributed in this case. So the mean of the forecast is going to be this. And then I will sample from a normal distribution, and I have a noise variable that I will need to learn from the data. But this is kind of decoupled from the transition. So as I will show later, there's some freedom about the things that you can do here that you couldn't do in the common cases. And then you just return the next level, which is the net carry, the next carry, and then the prediction. So you crack this. So how this, and this is the only NumPyro model that I'm going to show, once you have this transition, if you want to do this in a fully Bayesian way, you need to set priors on your parameters. So we know that this will be a function that takes the time series and the future, which is like the forecasting horizon. By default, is 0, meaning that I want to do inference. Tmax is the maximum, let's say, the size of my time series. And then I have 3 parameters that I need to set priors from. So the first one is the alpha, or the smoothing. And I know that this thing has to be between 0 and 1. And for this example, and it's very convenient to use a beta distribution, which actually has the support between 0 and 1. I need like a init level, like an initial value for the latent variable, and I need a value for my noise. And if you think about like a Bayesian linear regression, this is typically what you do, and this thing has to be positive. Then you have your transition function that it was written before, And then NumPyro has this kind of cumbersome notation on which you condition on the data. You're telling, okay, the model, y is something that I've observed, so please run scan, assuming that I know y. Because if I don't know y, I just need to sample from this. So this is kind of the only if statement, let's say, that is the difference between doing inference and prediction. And we can actually use like Markov chain Monte Carlo to run this in a fully Bayesian way. And the example code that I show, I think I generate the data myself and then show how the parameters look. So you can do all the Bayesian machinery to evaluate your model and so on and so forth. And this is what you get. It's not very kind of amazing, but this is what an exponential smoothing level model would do in other libraries. So we have achieved a baseline. But in the same notebook, actually do a full transitional implementation of the damped exponential smoothing, and the code is much longer, but the essence is the same. You have the formulas for the exponential smoothing, you write your transition functions, and then you put it into the model. There's another typical use case, which is the ARIMA model. So the ARIMA model can have various components, but in this ARMA 1.1, we have like an autoregressive term. So we want to learn from previous data points, and a moving average, which is from the previous errors. And again, the model is relatively straightforward once we understand the transition function. So again, for the transition function, I have my carry and my t, and what I need to carry is the previous prediction and the previous errors. Then I have the R autoregressive part, which is phi times the previous value of y. Then I have the moving average part, which is the parameter theta, and plus times the error. And then I just sum this up. And this is the transition function. And then you can put this into the big model, and the plot below shows that the results that I'll get from, let's say, the point prediction of the stats models package actually fits the mean prediction of this probabilistic model, and you get these kind of credible intervals around the point forecast. But kind of in reality, a lot of, at least I was faced like to series that look like this. So they were like beautifully seasonal, but there are just a lot of zeros, and maybe just varying between 0 and 10. You are selling a very specific brand of yogurts. You probably don't expect this to be super high if you are starting in the retail sector, for example. So you could can try running ARIMA or exponential smoothing. That's fine, but there are better ways because you're probably going to be forecasting just 0 at the end. So within this intermediate time series models, there's a slew of things that you could do. I just want to talk about some techniques just to show how, if we have written the transition function once, we can recycle this. So if we have such a time series, what we could do, and this is what is called the Krosnon-like method, is to split the series in two. Because, I mean, this is essentially just 0 and sporadically some spikes. So we can separate this into the demand series, which are called set t, and the demand interval, which is pt. So, and from the initial time series, I create these two, and then I combine them together. Because I do a forecast for each of them. So the first series is I'm just going to remove the 0 values, and I'm going to keep the non-zero values. And for pt, I'm going to just take the times between the two non-zero values. So you have a spike here. I just get the time here. These lengths are going to define the second time series. And what I can do then is use a exponential smoothing on each of the components and just take the quotient. And if you think for a bit, this is going to be a pretty good baseline, because it's in essence telling, like, I don't know, there are a lot of zeros. What I can tell you is, like, I can try to guess the level, let's say, which range do they vary, and how often are they going to happen, and that's going to be my best guess. If I didn't have anything, I will bet my money on this. So from the initial time series, these are the demand curve and the period curve, and then you will need to run your exponential smoothing for each of them. But if you have done this once, you can actually recycle this, and you don't need to write everything from scratch, because if I have a file that has the exponential smoothing implementation, I can just call it within a NumPyro model. I just need to tell NumPyro, okay, the scope of the level model is going to be demand. The scope of this other exponential smoothing is going to be the periods, and then the model becomes very small. So in my journey, I realized that writing the components of the model once was very helpful, because I could then plug them as Lego pieces. So the thing was paying off. And there are various variations of this approach. For example, there are other TSV methods which change the way the P series is created, and is not taking just the times, but estimating like a probability of the times between two non-zero periods. And this thing is huge. Let's say the intermittent time series models is huge, and I could recover all of them. So that's fine, but you could be asking yourself, have we achieved something? Let's say I could have done this in maybe 10 minutes with stats forecast. So kind of this is where I started experimenting with things, just because why not? And within the TSV model, I had my transition function, but at the very end, I thought, okay, instead of running like a normal distribution as everyone does, what if I run like a zero-inflated negative binomial? So negative binomial just makes sure that every draw that I get is an integer, and the zero-inflated is trying to learn the process on which these zeros might appear, because why not? And this is one result of that experiment. The resolution is not the best, but you can see it in the notebooks or in the code. So I want to do like to evaluate this on the test set. So the crosstone forecast, this is like a one-step ahead cross validation, is just a flat line. So it's just gonna keep you like a flat line. The TSV model, which is this green one, drops much faster, because it's just kind of considering the fact that if it hasn't seen zeros before, it's going to predict zeros more confidently. And the TSV and the zero-inflated one is somehow in between. So you can start getting some different flavors of this, kind of weird time series model if you can just twist the likelihood. So that was just for the sake of me doing stuff, but let's go to a real business problem. So again, motivated by this intermittent demand. So one of the problems that I have is the following. I have apples, and I have oranges, and I have just 10 slots in my store. And then I could just have 5 oranges and 5 apples and sell them together. But if I see that every day all of the apples are gone, my sales data will be like 5, 5, 5, maybe 4, 5. And then if I wanted to optimize kind of the shelf, and if I do it through like a forecast model of sales, I will just forecast 5. But that's not giving us any information. And the problem is that what we actually want to understand is the unseen demand. I don't know what the demand is. I just know what the sales are. And once I sell 5, even if people want to buy them, they won't be able, so I don't know the potential. So what I did was like a very explicit data generation process on which I have the unseen demand in black upstairs, which no one can see except me, because I own the simulation process. Then I have the sales, which are the blue curves, which is fluctuating proportions of the unseen demand. Maybe the competitors change prices. There are other things that I don't control. So there's some sales that still are connected to the unseen demand. And then what I do is that I add two processes. So I randomly set points on which the availability goes to 0, just because they forgot to send apples. And I use a max capacity of the time series, which is around 2.3. And that's the orange line. So the orange line is actually the sales that I see. But I would like to know the black line, right? So one thing would be and I want to do a forecast. One thing is I could probably try to forecast the orange line, but I'm going to miss all of the information that was lost just because I went out of stock. So if I take my ARIMA model with Fourier seasonality on all the fancy stuff that you can get, you will get the green line as a forecast. And the true values are the orange ones, which are going up. And the green line, let's say, if you're thinking this as a pure forecasting problem, it's a decent forecast, but it will never capture the upward trend just because we have a max capacity. So no matter which time series model I throw to this, if it's just relying on the historical data and I don't tell anything to the model, it won't take the trend. Like, it won't appear from anywhere. So I hope the problem is clear. So I want to connect this with what is called censoring distributions, because what's happening is that if I collect the sales data, every time I get at the max capacity and I plot the distribution, it would look like this. So this is an example of a distribution that is censored. So this is like an example of a gamma distribution, which censored at 2 points, which I cut them, and I just have a lot of points out the boundaries, which are going to be the sales where I got the max capacity. And if you think this in the context of linear regression, this is going to bias the results. So for example, if I know that the blue line is the true distribution, but I just get the orange, it's going to be very hard to do it in a naive way. So if you do it by brute force, so to say, just fitting a simple model to the distribution, you're going to get the green against the blue, which in this case, it doesn't look that bad, but if you're thinking about sales and money, this could be actually very expensive. So there's a way of actually fixing this by using what is called this censoring distribution, and you can fix this. And you can recover the distribution, but you need to tell the model there are 2 points which are censored, and there's a trick for that, which I discovered from Kyle's blog post. So here's the trick. I don't want to talk about it. But once you have a censored normal distribution, the only thing you need to do in your exponential smoothing or ARIMA model is just change the likelihood. And don't use normal, but censored normal, and it's going to work quite nicely. And by the way, because we all love open source, I wrote a tutorial on NumPyro, so you can check it on NumPyro documentation just to make this more welcoming, so you can look into the details. So that's why I don't want to spend more time. And if you actually add the censoring distribution, the predictions are the purple one, so they actually go up. Just because the model was actually learned, or let's say was able to learn, that all of these points reaching max capacity was at a point which had potential, probably. So it doesn't cut the forecast, but it allows this actually to eventually grow, and then I compare it against the green line, and let's say this is really, really good. But there's always a problem because I will never see the unseen demand. If I don't change my capacity, if I do like a naive train test split, I would be always forced to take the time series model in green. So this is like a feedback loop of just bad decisions, because you don't see the demand, you just keep predicting that, and then you're happy with that prediction because you don't see the potential. So that's why it's very important within these forecasting problems not to be tied to just a model metric, but a business metric. Because if part of this analysis was, okay, let's change the distribution of our products, and we see downstream that revenue increases, then we're all happy. No one is happy if we just improve a vanity error metric in the model. So this is one of the cases where I see probabilistic models as having pretty good opportunities in the industry. So you can now think about the possibilities, and one typical use case of a Bayesian model is hierarchical modeling, on which you have many series and you have, let's say, three options. You can model them, all of them independently, you could model them, all of them together, or you can actually take the hierarchical structure in consideration and make sure that within meaningful groups you can pull information from one group to the other. So just 1 second. Just okay, we're back.
Don't touch it.
Yeah, stay there, stay there. So this is a relatively like a medium set data set, like just 300 to 500 time series that I took from a package that I'm going to talk about later, and it's about tourists within cities, and also the reason behind the purpose of the trip, like it's holiday, business, or whatever. So what I saw is that at a certain point, there was a trend component coming from the region. So depending on the region, there was a sporadic trend coming. So I thought, okay, let us try to use the exponential smoothing model, but instead of having them all together, let's, for the sake of whatever, fun, let's assume that the level on which the trend and the level combine is actually hierarchical. So they don't depend on just one series, but it's coming from the region. So I did this, and again, the model looks very, very big, but it's just because of these transition functions. And this is one specific example on which the results look interesting. So the blue line is my time series, and if I would forecast this, I don't see any trend component. It's going to be just like if I wouldn't show you the other thing, I guess you will bet your money that there's no trend. But as I'm running a hierarchy on the regions, the orange line is actually going up. The purple one, which is, let's say, whole winter exponential smoothing, like the classical one, steeps flat. But the hierarchical model is actually capturing this because it's seeing from other series in the region that things are going up. So again, think about that you have sold red apples for a year, and then you want to sell green apples. And then you tell your stakeholder, we need to wait a year to get data. And he tells you, but we have sold apples in the past. Like, yeah, but they are different apples. So this is motivated in the problem that even though products can be different, if they belong to a hierarchy, you can pull actually information from similar products, and depending the use case. So there's a nice metrics that is called CRPS in probabilistic programming. I don't want to talk into that. And I have two colors here, which is actually the telling if I evaluate this point estimate, yes or no. So let's focus on the point estimate, so forget about the blue lines. So we do see that the what I call nuts and SVI mean, which are the exponential smoothing models, do slightly better than the auto ETS from StatForecast. And I would say it's essentially noise. So even though this thing looks very fancy and for a particular time series worked very well, on average, it was not that kind of game changer. So I guess one key point of this slide is that in spite of the fact that all of this sounds like very cool, classical time series models are hard to beat. And you should always compare this against, okay, we beat the seasonal naive, this is great. But again, thinking about the application, think about the metric that you care, whether it's like a model metric or like a business metric, but never throw away your time series model. The second point about this slide is that I have two kind of prefix like nuts and SVI. So nuts, it's essentially Hamiltonian Monte Carlo, so it does the whole Bayesian MCMC inference, and it can be expensive. There are tricks to speed this up. This can run on GPU and so on and so forth. But in general, for really large problems, thinking about 10,000, 100,000 time series is probably not the best idea to do this at the first glance. There's an alternative which is called stochastical variational inference, and NumPyro provides this kind of in a very nice kind of API. And you turn this problem into an optimization problem to some degree, and then this runs really fast. And at least in this example, there's no sacrifice in going from nuts to SVI. This is the blue line where I do evaluate the whole posterior. In some cases, if you have hierarchical models, SVI can bias the results. But if you need to start and you want to experiment, I think it's fairly easy to take one of these classical time series models, just add the hierarchy, and run SVI. It's a good start. Don't do MCMC on such bigger data set as a first iteration. And lastly, something that I want to talk about what I'm doing today, or let's say in the last weeks, is pricing models. So this is not in the context of, let's say, pure forecast, but in general time series analysis. So you have your apples, and you need to price your apples. And you need to make sure that you balance, let's say, you want to have a high price because you want to improve your margins, but it shouldn't be that high that it hurts sales. And you also need to optimize, let's say, the distribution between apple and oranges. And just with these two fruits, it can get very complicated. And one of the things that we are interested in setting good prices to products is price elasticity, which is essence trying to answer the question, what's the price sensitivity, let's say, how sensitive to the price is a product. So in a nutshell, what you need to do is to take your price data and your sales data and run a regression. And there are various challenges with that in practice, because on the one hand side, prices don't change that much. So if you have a business where you care about price perception, or you don't, or let's say you don't want to give opportunities to your competitors, you want to make your price very conservative, which means if you want to run any type of regression, you need some variation. And it's very hard to convince people, let's say, hey, can you just move the prices a bit so I can get noise from my regression? That is very hard to sell. So this is one problem. And the other problem is that, in general, you have very little data, especially for new products. So what I found, which is very useful, is actually run these elasticity models, but use the whole hierarchy. Because most of the times you have hierarchies for the product. So an apple is a fruit is a fresh item, and so on and so forth. And by doing this and controlling also for the time, and let's say you can custom these models quite good, you can get really, really nice estimates, which actually makes sense. So you can check this online, where I compare like a naive elasticity model with a fixed effect model with a hierarchical model. I talk about endogeneity. And the end result is that really these hierarchical models for these time series problems can bring a lot of value. So this is, for example, the type of results that you get, that you have individual elasticity estimates for each product, and then you have a whole elasticity estimate for the category. and that can be also very useful because maybe you don't want to kind of have pricing policies at the product level, but more at the category level. And in practice, yeah, this actually works pretty well, so check it out. So I would just want to end with telling that all of these concepts can actually translate it to other probabilistic programming frameworks. So this is really about the concepts. So I've also pushed with a couple of other PyMC developers an example on how to do like a time series with like ARIMA-like models in PyMC. Again, the main component is the scan. So if you understand scan, then this should be relatively easy. And we do a big discussion about, let's say, conditional forecasting and how this fits into the data generation process within the PyMC setting. So please check it out. I'll send the link. And very recently, there was a webinar where one of the core developers, Jesse, talked about the new experimental state space model. So a lot of these things like the exponential smoothing, the transition function, is something that just someone would need to write once, right? Like you probably don't need to write this every time. So you either check our code and just store it somewhere or just use the model. So this lies in a library that is called PyMC Experimental. So it's a little bit hidden, but it's there. You can actually install it with PyPyro. And then there's like a structural time series model. And all of the boilerplate of these things that we had in NumPyro are baked in. And you can have like a slow trend, seasonality, exogenous variables, and errors in, I don't know, let's say 4 lines of code. You have your time series model, and then you can plug it into a bigger PyMC model. So it's still under development, but I think it's very, very nice. And the examples that are shown in this video are really impressive. So there's a lot of potential, again, on real applications. Yeah, so you can find the slides online, and I collected some material that could be useful for you to get into this topic. It was for me, so I hope this, if you are interested in this topic, can be like a good guideline to where to start. Yeah, there are a couple of papers, and of course, two other packages which might be relevant because touch forecasting or probabilistic modeling in one way to another. That's it. Thank you very much.
Okay, thank you, Juan. It was a very insightful talk. And it's time for questions. Please raise your hand if you have any questions. Yes.
Hi, thanks for the very interesting talk. I just have a question about the example when you say when we don't have the data for the red apple and we want to.
Sorry, can you repeat that? Can you repeat when we don't have data for what? Sorry.
I mean, just about your example about the red apple and the green apple. When we don't have data for the red apple and we want to make the prediction or the forecast for the green apple, could you elaborate more how to use a hierarchical modeling to do that forecast on the green apple when we don't have historical data?
So the intuition would be, for example, if we take an exponential smoothing model, there's one parameter that we care about, which is the smoothing factor between the level and the time series. There's just one thing. And I would learn this from red apples. So one thing that I could do is just copy-paste on that. But I guess alternatively, what I could do is once I keep collecting more data, I can then make a mix, right? Like I keep collecting, this is a weighted average on the, let's say, length of the time series. At the moment, I don't have anything, I could use that, but once I start collecting more and more data, I can refine this because it could be that red apples and green apples sound differently. But if I don't know anything, I can just set this up at the beginning and then refine this as data comes in.
Yeah, okay, I see, thanks.
More questions? Yeah. thanks for your presentation. I really like this example where you showed kind of like the sensor data set, as you will. So I guess that you can make a simulation and you can validate how well it works. But how would you do this if you actually want to forecast a data set like this? Because if you do a cross-validation, for example, you want your model to forecast higher than the actuals, right? You want your model to also censor to forecast also the censored part. But then if you want to validate the accuracy, then you cannot see the centered part, of course, because you also don't have this in your validation data set. So how do you deal with that?
So this is something that I'm trying to figure out myself, because I think this has also to do with the process. Because, for example, let's say I cannot just simply do like a naive validation, as you said. So one thing that we are experimenting with is, for example, shift the shelf distribution based on what we get, right? If we are seeing a lot of max capacities, then we can tell, okay, actually there's potential for this item to be sold more, for example, if the oranges are not selling. So we can just change the distribution. In practice, to be honest, I'm trying to figure out this out. I guess at the very end, we care about the business metrics. So for example, let's say if I was selling 5 oranges and 5 apples were always gone, and the oranges there, based on this analysis, we'll forecast, okay, we'll think that having more apples is better, then we'll change the oranges for more apples, and we see a revenue increase. So it's a little bit more complex, but I think it's in this direction. This is something I'm still trying to figure out myself.
Yeah, thank you.
All right.
Hi. In the beginning, you were talking about the scan function. As I understand, it's sort of based on the jacks underneath. And I think what I understood what it's doing is that essentially it's scanning, or it's like tracing the behavior you outline in Python in this function, and then it does some just-in-time compilation. Did you ever run into sort of the boundaries of that system? Like, I don't know, when you're using external libraries inside of that function, or like when you do more complex operations, does it have trouble actually executing that, or sort of, yeah?
So I think with scan, there's like a really love-hate relationship. I hated that function for a long time because I couldn't make it work. And if you want to do like a weird recursion, doing it a for loop is really fast, but with scan, it was a pain. I guess once you kind of understand that, and that's kind of a moment where it clicks, then it becomes really useful. So why is it necessary? It's because you are not passing just data, but also distributions. And that's why each probabilistic programming language like PyMC and NumPyro need their own kind of version of it. So yeah, having dig into the internals, it's a little bit of a mess at the beginning, but once you get it, it can be very powerful.
Okay, I would like to thank him with a gift from PyData.
Oh. Oh, cool. Thank you very
Please
much.
join me with big applause for Juan.